Hello, welcome everyone to this symposium on emerging contaminants. We are going to give a couple of seconds for others to join, and we'll get started very soon. All right, let's get started. This is a symposium on exploring emerging contaminants, particularly focusing on risk solution and policies. I just want to introduce our panelists. Um, our first panelist is Dr. Chuck Gerber, professor of environmental sciences in the University of Arizona. Um, uh, he'll be introducing some of the concepts on one of the topics in emerging contaminants. We also have the Dr. Mariana Lanzreni Lopes from UMass. And finally, we'll be having also Dr. Monica Hubbard uh, from the Public Policy and Administration, Boise State University. So with that introduction, so general overview of today's topics are I will be starting off with giving a general overview um, of the topic, and then followed by the panelists presenting. And of course, you can save your questions to the Q&A session, but feel free to uh, add your questions to the chat box, and we will be glad to answer your questions. So let me start off with mine. So to start off and give a general overview, I think it might be familiar with many of you, but I think I just for those who are getting initiated in this topic, I wanted to have a quick overview of this topic, and also I'll be highlighting some important emerging research in this area. We'll be I'll start up with some sort of what do we mean by the emerging contaminants, primarily those which are of recent sources and which have some new pathways and sometimes having uh, perceived or potential threat in terms of the human health and environment. So we differentiate from the conventional ones, and of course there are a variety of sources um, which contribute to these contaminants. So these are some examples of the grouping of these emerging contaminants from a variety of pharmaceuticals, personal care products, um, endocrine disruptors, and you can see some of the examples listed on the right side. And again, these are the source of some of those information is listed in the bottom of the screen. I just want to give a quick overview of the history behind. It's all started in 60s with heightened awareness um, with Silent Spring publication and PCBs starting to emerge as a highlighted organic pollutants. In 80s, non-conventional pollutants, especially pharmaceuticals, heavy metals, petroleum derivatives are all starting to be identified in some of the water bodies, and the EPA has been recognizing them for need for monitoring. In 90s, there were more advances in some in analytical methods in identifying these some of these contaminants. In 20s, the term emerging contaminants start to get popularized after some publications, um, um, and and primarily um, in 20 slowly there are variety of emerging contaminants had been researched in terms of their bioaccumulation and persistence. And more are added to the system, especially microplastics, antibiotic-resistant genes, and it has been in a highlight of the global conventions on how to deal with these emerging contaminants. And finally, in 2020s, we have seen emergence of methods like nanotechnological methods, bioremediation, or advanced treatment methods. And research is also on persistence and also influence of climate change on contaminant transport. And it has been a part of this One Health approach linking ecosystem and human health. So with that, we are seeing, so here is another study recently on the concentrations of a variety of emerging contaminants at a continental scale. So we are seeing uh, many of the countries and continents are having this as a big issue. And in terms of the trajectory of research itself, until 2020, there has been increased detection, assessment methods, a variety of methods to accurately detect these contaminants. And um, in terms of this is a bibliographic assessment on how our research has been published. This is from 2010 on. Much of the research has been so all the notes you see are the extent of how much research has been, and then also it reflects some of the collaboration among countries in studying emerging contaminants. So a variety of pathways. Again, this from Rauch et al. In 2021. You can see that it expands from industry to domestic, livestock, agriculture, hospitals, and in addition to wastewater treatment plant, but you also have landfills, soils, and impacts on groundwater and surface waters. Aquatic impacts, again, so here is the bottom variety of emerging contaminants, and this research from Parida et al. In 2021 on how different aquatic communities are impacted, and this is the risk coefficient for each one of the emerging contaminant. This is just a summary of studies on 7 contaminants affecting drinking water supplies, and much of them are when you see this X is a documented evidence, but this is again dependent upon what research has been done on the water supplies. And the documented evidence, you can see that the cross-cutting issues from aging infrastructure to climate change to disparities, all the way to private well contamination, and how each one of those contaminants are documented. Here is another interesting dimension related to treatment revenues, especially biotechnology. So it has been increasing in the global market and we are seeing all those variety of approaches we use have a growth rate highly also dependent upon the cost of that particular technology and the implementation. So here is some publication trends related to solutions and how they are actually starting to emerge as unique. So for example, on the left-hand side, we see from activated carbon to biochar, the oxidation process. On the right side, it's primarily the number of patents which are being developed, and it has been exponentially increasing as a research interest over time. The emergence of tools, primarily on innovative methods in terms of bioremediation. So here is some sort of a conceptualization of how research and development is emerging in this field. So you can see that the field itself is both both on assessments and changes in some sort of a technologies, but also policies and public health implications assessment and regulatory decisions. So quick overview, I'll just quickly go through some of the advanced the methods on how we are approaching from nanotechnology, membrane filtration, advanced oxidation process, um, bioremediation, focusing on microbial or phyto remediation methods, sensor developments, and so much of the research on IoT or Internet of Things, enabled sensors to all the way to small scale user-friendly kits. Emergence of green chemistry in terms of non-toxic use of non-toxic materials and also eco-friendly alternatives. At the policy side, trying to actually have a circular economy model to approach some of the resource recovery and wastewater reuse. In terms of public policy and public engagement, having adaptive policy frameworks or development of public awareness campaigns, especially citizen science and a variety of aspects to manage the risk. And finally, in terms of using the large data models like machine learning and AIs in assessing risk and approaches. And finally, there is a big emphasis on decentralized treatment systems and participatory type of research in addressing emerging contaminants. So with that one, I will stop my introductory presentation, and I wanted to pass it over to our next speaker. Chuck, do you want to share your screen?
Yes, here we go. And oops, did that work? And can you see the screen?
Yes.
Can you see the slides okay?
Yes.
Okay, let me just slide show. Okay, I got it. Thanks for the introduction. Sorry, my background I haven't adjusted yet, but a lot of the interest in water and water reuse in Arizona is having enough supply actually for agriculture. If you're having a salad today, there's a 90% chance some of the produce you're eating came from Arizona. We produce 90% of the leafy greens in the winter in the United States. So water and water quality is a big issue in Arizona, where we have a limited supply and no new real resources of water and that. I'm located at the Water West Center, which is a research center about 100 yards from an advanced wastewater treatment plant that was set up by the University of Arizona in conjunction with the local utilities to look at issues as they arise with water and water reuse. And I'm largely going to be focusing on two aspects of microbiology. One of them is distribution systems. The interest in distribution systems is because they're now believed to be the major cause of waterborne illness and disease in the United States, largely because of the presence of biofilms in the distribution system. CDC, Centers for Disease Control, estimated that there are about 10 to 12 million cases per year of these distribution system associated water supplies. Pseudomonas being number one, which surprised a lot of people, but it's largely skin, eye, and ear infections are what they cause a lot. And then Legionella has seen a dramatic increase in recent years. And Mycobacterium, all three of these are actually Legionella and Mycobacterium are more resistant to disinfectants, and so they can survive in distribution systems with regular chlorination levels that are usually present. Pseudomonas, along with the other two largely inhabit the faucet area or areas where the chlorine levels are lower, but they can grow very rapidly in any moist environment. And these are the three that are very difficult to control. Actually, Legionella and Mycobacterium have been selected for with the use of chlorine and chloramines in distribution systems because they're more resistant to the chlorine and disinfection. And so you really, every time you change a disinfectant, something to think about, or change a treatment process, another microorganism will dominate. Another risk will be developed from another microorganism. Microorganisms are very adapted. Legionella, before we had hot water, was probably not a problem at all unless you went to a thermal spring or something. But by creating hot water distribution systems, we made Legionella a problem in the world. One of the things to think about what we mean by microorganisms being opportunists. The other issue, and particularly in the Western United States, is direct potable reuse. It's created a lot of interest. Recent work on this indicated virus levels are much greater than we previously thought using molecular methods, about 10 to the 10 per liter now, we believe. Previous work had indicated too that enteroviruses, certain groups were more dominant than others, but now we realize the enteroviruses, which are largely been studied, are really a small minority of all the viruses that are actually present in wastewater. Removal is large. California now is requiring 20 log removals for direct potable use from wastewater to drinking water. And each of the log represents a 90% reduction requirement. And they only give any treatment process 6 logs removal credit. So you got to have at least 3 to 4 processes in there capable of removing 6 logs of viruses. Viruses are the most difficult contaminant to remove. You have to get it down to less than 1 per 100,000 liters for rotavirus. That's less than 1 attogram per 100,000 kilograms. So it's a real challenge. You can't measure that level. 2,000 liters is about the most we can process. So you have to model that. So you have to make presumptions of your ability to remove the viruses to that level. Sequential treatment steps to remove viruses have always been added, like 6 logs for chlorine, 6 logs for ozone. Recent work indicates, and I'll show you why, they're not additive. You cannot do that with naturally occurring viruses. The dominant viruses in advanced wastewater treatment now, which involve several steps of treatment, are the adenos and reoviruses, which are the most difficult to remove, we're finding. Certainly in our work and other recent work, 95% of our isolates in advanced wastewater treatment systems after treatment are the adenos and the reovirus, both double-stranded viruses. So they seem to be more resistant. And they've largely been ignored because, and I'll tell you why, work done 40 years ago indicated that these were the most sensitive viruses to disinfectants. And it's turning out they're not. Just to give you an idea what's going on with Legionella and why organisms growing in distribution systems are important is the trend in increasing number of water outbreaks associated with drinking water with distributions. Legionella has really seen an increase. Now there's more monitoring than there used to be, maybe one reason too, but you can see a general trend, and that's believed to be for a number of reasons. Disinfectant residuals are selecting for Legionella. Stagnation in distribution systems like over the weekend in a household or a facility or a business, it creates stagnation where chlorine levels decrease, and so you get increasing growth of these organisms potentially in the distribution systems. And bacterial levels from utility increase more than 100-fold when you go to a home or distribution system. In other words, even if you have a very low level of Legionella or none at all that you can detect, by the time you get to the household or a facility building, you'll get a 100-fold increase in the number of bacteria, just heterotrophic plate count from studies that we've done. Because of distribution systems, there's stagnation is an issue, and they're not maintained by the utility, they're maintained by the household. So there may be issues with maintenance of distribution systems in the household. The other thing is we have an increasing number of special populations. Elderly are very susceptible to Legionella. Almost all the cases are people over 50 years of age. So as our population ages, you get an increasing number of individuals who are susceptible to these distribution system microorganisms. And we have more immunocompromised people because of the drugs we use to treat many types of diseases that immunocompromise you. So you have a much more susceptible population that you have. So it's becoming an increasing issue for that reason. Now, issues with microbial by treatment, I think I want to point out to you, particularly when you get to water reuse, is microbial biodiversities. Microbes are individuals. No two, even of the same type, are the same. So in other words, one individual in a population may be more resistant to the other, even though they're the identical species. Just like if you take 1,000 people to swim the English Channel, only 10 will make it because they're fit, and we're all human beings, and that's the same thing with microorganisms. I'll show you what that means in treatment. Larger numbers in the water indicate greater diversity. Small differences in chemical makeup of a virus and its structure, even though they're the same virus, can make a big difference. And one of the big problems we have is most of the work that we do on removal of microbes by treatment processes are done by growing up a laboratory strain, putting it in a beaker and doing a test, or using a pilot plant system. And I give you the example of we've done a lot of work with MS2 bacterial virus for evaluating system, and we really know how to remove that virus, but not all of its relatives in the distribution system. And Carl Linden recently showed that adenoviruses, naturally occurring ones, are twice as resistant to UV light as the laboratory strains, which makes a big difference in the amount of dose you might want to use for a distribution system, largely because most of the data we have been previously based on laboratory strains, not naturally occurring strains. And microbes evolve. The same microorganism you find in the distribution today may be a different one than tomorrow. Even if you do a lot of monitoring, you'll find reoviruses dominate one day. Next week, they don't, and then they come back again. And we're probably looking at differences in the makeup and resistance of individual types. One of the things we do, we model beyond the data set. We gather data on disinfectant efficacy and then model it out, or treatment and model it out. But we don't really have data to know it's a straight line or how that curve changes. Variability of treatment processes become an issue. If you monitor treatment processes on a regular basis, you'll see variability. You don't always get 90% removal. Maybe you do on Friday, but on Sunday you get 50% removal. It varies a lot if you start looking at large scale treatment processes. In scaling, going from a pilot plant where you make decisions on doses or treatment processes don't necessarily mean it works on a large scale system. I think that's one of the deficiencies that we've seen. This is one of the reasons it makes removal of microorganisms challenging, is they tend to be inactivated by disinfectants or removed like seed. You get really good removal. Maybe you'll get about a 5 log removal, 6 logs, and it flattens out. You end up with a population that's different, that's very resistant to the process and removing it. And when you evaluate treatment processes in the lab or pilot plant, people are always looking at this. They're never looking at this for the next treatment step. And I'll show you what that means. In recent work we've been doing, a lot of the process is designed largely for advanced treatment to remove 12-log removal. This is for the adenovirus in one cell line. Secondary treatment after chlorination, we found we got a 3-log reduction, but then they ozonated again, and they only got a 2-log reduction. And then they got a log reduction by carbon, and by the time they got to UV light, they were only getting a 1/2 log. What you kept doing is selecting for the most resistant organism. So Superman microbes are left here by the time you got all of the weaklings allowed. So they only got 7-log removal, not 12 that they were expecting. They were expecting, at least 3 logs by UV light, and they couldn't get it because they selected for the most resistant organisms. Let me show you what that means in another process I want to highlight. We've been looking at colophages, naturally occurring ones, because you can measure a 12-log reduction with the levels. You really get a good log removal here with these naturally occurring somatic colophages, maybe 5 logs. But after microfiltration, after reverse osmosis, and even after advanced oxidation process, which is good for chemical removal, we don't see anywhere near, if you put it at the end of a process, 6-log removals. We're just not getting it. And one of the reasons I will show this too is to point out what RO membranes, reverse osmosis. A lot of people think viruses can't get through those, but we've evaluated a lot of full-scale systems, in about 2 to 3 log removal for some viruses is about the best you get. Now, engineers will right away tell you it's due to leaky seals, but the only leaky seals I know are marine mammals with a bladder problem. All RO membranes will allow the penetration of viruses into you of it, largely because we're looking maybe at very low levels here, maybe only 1 5 per 100 liters, but we can measure that. And it's difficult to correlate that with a chemical remover, or 1 virus per 1,000 liters. You can even go, but you can't really depend on RO systems to give you more than 2 or 3 logs. And one of the reasons California only allows a 2 log removal credit for viruses, and that it's something people should be aware of. There's a lot of variability we've seen in RO large scale systems to remove viruses. Um, the other thing is what we've learned is chlorine contact or disinfection contact things may have been greatly underestimated for viruses. Laboratory suggested studies done over 40 years ago, and some of them more than that, that Rios and adenos were the most easy viruses to kill by chlorine and other disinfectants. However, they only one cell culture passes. That's where you grow the viruses in cells. And recent work indicates that if you pass it 2 to 3 times, in other words, you expose it to cells for like a week, and then you pass it for another week, and then another week, that you increase the titer. It may be tenfold by doing that. And so many CT times, for at least for adenos and Rio in all viruses, may have been off by tenfold or more. And the other thing, you throw in naturally occurring viruses being more resistant, maybe double what's been used before. CT times have probably been greatly estimated. And then it depends on the water. Most of the adenovirus work was done in buffers. And when you compare a buffer to the real world, you add another tenfold. So CT times may have been greatly underestimated that we currently use for water and advanced wastewater treatment. Um, I think this has largely come to light because of the newer technology in microbiology. So what do we really do with all this? Well, we need new strategies for control of bacteria and distribution systems. Yeah, treatment at the tap is one option. Certainly, I think that's a good option for healthcare facilities. It's difficult to manage the organisms and distribution systems because of the resistance to chlorine and or chloramines that are used in some systems. So I think some type of treatment at the tap. A lot of healthcare facilities use membrane filters now to remove bacteria, or some type of treatment, UV light at the tap may be called for. Or regular flushing is the other thing to produce stagnation. That seems to be another option that could be used. And I think monitoring is coming in now in healthcare facilities for Legionella. I think really some type of monitoring for Legionella at healthcare facilities is necessary to make sure you have the control places. You have a control facility for Legionella, I think is really needed. I really feel monitoring is essential to really know what the presence of Legionella is in their distribution system, and that at least on some basis, doesn't have to be every day, but you need to really make sure that the control measures you have for Legionella are really working. I think that's true with any microorganisms. It's just hard, difficult to always correlate with disinfectant residuals and your risk from a microorganism, particularly in a distribution system. I think advanced treatment systems are going to be challenging from what we're seeing with the recent data that we're collecting. I think we can't really get around with some kind of a monitoring for virus removal. Maybe bacteriophages could be used as the key, but physical chemical monitoring systems are just not enough to do it when you're talking about risk of from organisms in thousands of liters. You can't really measure chemical relationships or physical relationships with that. And even small variations in variability in treatment processes need to be recognized, because even a small difference in CT time can make a big difference in finding viruses after treatment from what we're finding out. And your ability to measure things like CT time adequately to do it. I mean, you have to, when you're measuring a CT time at 100, let's say, or 40, which is often used here, that means 99.9999% of that water has to see that CT time for me not to find a virus, because we can measure viruses in 100 liters easily. And I think it's going to be a real challenge to develop systems that adequately indicate the variability in your treatment systems, and you're actually getting the amount of treatment. So I think this is critical when you're going toilet to tap, as they say, or wastewater to drinking water. You have to have assurance, or you have to have a buffer zone that allows you to do some type of monitoring, a routine monitoring. It doesn't have to be the thing you have to do every day, but you need to really have the assurances that the treatment systems you put into place are always working, and don't take it for granted that they're always working or removing the organisms you're concerned about to the level you're concerned about. It's hard to get away from not doing some type of microbial monitoring because of the sensitivity of the technology and the requirement for the removal levels that you need so you don't have a risk of transmission. Hope I got that in enough time to do. But that's it. I have some real challenges, I think, from the microbial standpoint with the technology we have now available to measure microbes is going to be a challenge in the future.
Right. Thank you, Chuck. We might have some one or two questions we could ask Chuck, but you're welcome to add to the chat box related to this presentation. Chuck, could you unshare your screen?
Yeah,
Okay.
Yeah, got it.
All right. So our next speaker in line is Kiron Shekawat from University of Massachusetts. Kiron is standing by for Dr. Lopes, who lost a voice. But without further ado, Kiron.
Thank you, Kim. Let me share my screen. By the way, my voice also kind of challenging. I hope it will not be a problem for you to hear. You can see my screen?
Yes.
Thank you. Thank you, Dr. Garva, for your wonderful presentation. I really enjoyed it. Hello, everyone. I am Mohammad Shakhawat, aka Kiran. I did my master's and PhD at UMass Amherst under the supervision of Dr. David Rakau, and now I'm a postdoc in Dr. Lopez group at UMass Amherst. Today, I'm going to talk about the advanced treatment technologies for PFAS and the quantifying PFAS using the LCMS method. So I'm going to talk about what is PFAS and the quantification method of it. I'm also going to talk about the treatment processes and also the research and collaboration happening in UMass Amherst, also the challenges of quantifying PFAS in the lab. So without further ado, I'm going to talk about which is the PFAS is a perfluorinated compound, very stable and widely used as fluoropolymers, mainly in firefighting items. And the human toxicity is still uncertain. If we look for the source of PFAS, the earliest stage, the industry heavily used PFAS or produce PFAS are contributing to the PFAS to the environment. More recently, home use products like the takeaway containers or the strain resistance like clothing, carpets, leather goods, or non-stick coating or products like cookware or cosmetics. Unfortunately, the secondary source of PFAS contribution to the environment could be landfill and also municipal.
Kiran,
yes.
We are seeing your outline.
Okay.
I don't know. I think you have to switch your
Let me see.
view, I think.
Sorry.
It's down in the bottom right-hand corner.
This one?
That's the one.
Yeah, I did it though.
Wow.
Let me try one more time. Sorry for that. It's technical difficulties always.
It wouldn't be a Zoom meeting without some technical difficulties.
Yeah. It's always me, right? Okay, let me see. I can try one more time. I did. Now you can see my introduction page. Can you see my move the slide now? Second slide.
No, it's still on the outline mode, you know.
I'm sorry.
Well, I think, yeah, now we are seeing the second slide. Yeah. So slideshow is not working for you?
Let me
Oh,
see.
there, yeah, that one, try that. Click on that.
It's coming now.
Yeah, it's actually the presenter mode. It's in the presenter mode, you know, so we are seeing the outline, and I think probably you are seeing the main presentation. But, you know, that's okay. I think if you want to go one slide at a time, you know.
Like this way.
Yeah, that's fine, you know.
I'm sorry. I think maybe the animation giving the hard time. Let me see. I can make it a little bit. You're right. There will be always something. So maybe if audience would not mind to see that way.
Yeah, that works.
Okay. Sorry for that. So this far we talked about this one. Let me rephrase a little bit to catch up what I left. You can see my third slide.
Yes.
Okay, so I talked about how the PFAS is a fluorinated compound, which is stable and used as a fluoropolymer, and the human toxicity is uncertain. I also talked about the source of the PFAS, early stages, which is contributing by the industrial sources as producing the PFAS products and also use the PFAS. More recent is the home use, which is the food packaging, takeaway containers, or like clothing, or the non-stick coatings, which is cookware, or maybe the secondary sources, which is landfill or the municipal waste and septic systems. So if we look for the environmental toxicants and compare with other environmental toxicants, we can find the half-life of the PFAS is more than 10,000 years. That's why we are calling PFAS as a forever chemicals. So currently EPA are imposing the regulation for 6 PFAS with maximum contaminants level with MCL, the PFAS, PFOA, PFHXS, PFNA, PFBS, and Gen X. So if we look for the standard imposing that the goal is for 0 PPT for PFOA and PFOS with a maximum contamination level is 4 PPT. If for the PFHX and Gen X and the PFNA would be 10 PPT, whereas the hazard index for rest of the 5 would be the 1. So if we look for the nomenclature of the PFAS, the PAR means when all the hydrogen are substituted by the fluorine atoms, and the poly means if at least there would be a 1 fluorine atom. Means if we look for the perfluoroalkyl acid, which is the carboxylic acid, for P4 would be an example for C8. Perfluorosulfonic acid, which would be an example of PFOS, also C8. There will be many others too. But if we look for the definition of the PFAS, based on the OECD, which is the Organization of Economic Cooperation and Development, saying any chemical which is at least a perfluorinated methyl group or perfluorinated methylene group, that could be PFAS. But based on the EPA, there should be an adjacent 1 carbon, at least partially fluorinated. So if we look for the bottom like compound, which is the perfluoro 357 trioxooctanic acid, OECD saying is a PFAS, but EPA is not saying is a PFAS. If we look for the family tree of PFAS, most of the study to date are focused on the longer chain carboxylic acid, which is a PFOA, also the longer chain of perfluorosulfonic acid, which is PFOS, along with their major precursor. Now also study are focusing on the replacement compound or emerging PFAS contaminants, example as Gen X and others. If we look for why PFAS are forever chemicals, and we have to look for the physiochemical properties of the PFAS, because of the high solubility in water, low volatile and low reactivity towards the oxidants, that makes the PFAS as forever chemicals. So now I'm shifting my talk to the method of quantification of PFAS from the PFAS definition. If we look for the quantification method, there would be two ways we can quantifying the PFAS, which is a specific component analysis using LCMS, and another is the group analysis using the time of peak electro-osmotic response and time of flight. For the specific component analysis using the LCMS, EPF approved the method is 537.1 using 6 to 18 compound, which individually quantify the method. If we look for the group analysis, it tells a particular category of the group where it can degrade for a simple compound, or it can be applicable for all PFAS using the time of flight. Now, in UMass we in 2020 developed a direct injection method which can quantify 28 compounds using a high responsive UPLC with tandem mass spectrophotometry, LCMS. And for that, we impose the method ASTM-D 7979. For that, we use some of the technique to do the direct injection, though now EPA moved to the SPE method, the solid phase extraction method 537.1. With that, I'm showing some of the chromogram done in 2020 at UMass as a direct injection method for those are the compounds. We talked about for 28 compounds. With that, I'm shifting my talk to the treatment processes for PFAS. Here, I want to highlight three color shade, which is the the removal, which is the shade of 10%. The shaded removal implies 10 to 90%, and the black one implies the 90%. If you look for the conventional treatment process, which is aeration, coagulation with flocculation, sedimentation, granular or microfiltration, along with dissolve or flotation, the removal of PFAS is around 10%. While we also widely know that the ion exchange or the granular activated carbon can remove a significant amount of PFAS, but some of the element of the PFAS cannot be removed like efficient way, the way the nanofiltration or reverse osmosis could do. But the nanofiltration and reverse osmosis are so expensive that put a significant economic strain on disproportionate, marginal, and disadvantaged communities. That's why the UMass in our lab, we in Dr. Lopez lab, group are significantly invest time on doing the novel research on UV photolysis, UV AOPs conjunction with hydrogen peroxide and other advanced oxidation processes. And also Dr. Madby's group, we are investing the time to find out the electro-oxidation processes to destroy the PFAS. If we look for the GRAC, the study showed that the coal base are better than the coconut base. GAC is much more effective to remove the PFOA and PFOS based on the rapid small scale column testing. If we look for individual performance removal of PFAS compound by GAC, the shorter chain compound like PFBA will elute earlier compared to the longer chain, but also the sulfonate, which is the PFOS, are more absorbable compared to the carboxylic compound like PFOA. If we look for the break-even point using those GAC, we found a study showed that the 70,000 bed volume is around the bed breakthrough point, and it can we can replace the GAC partial, and then as a whole, after that period, we have to change the whole GAC bed. The green rectangular showing the shorter chain, and the sulfonic group is the pink one, and the hollow one is the PFOS. If we look for the break-even point, the cut is eventually become exhausted, which also we call the break-even point at some point, where the fraction cannot be removed efficiently anymore by the PFAS for the gap. Sorry. Now, for the ion exchange, it can do dual action, like it can do the ion exchange and hydrophobic interaction, but again, it's significantly expensive. So oxidation of PFAS also a challenging one, but it can be effective with UV and titanium dioxide. Here in Dr. Lopez group at UMass, we are investigating the efficiency of the UV with titanium dioxide, UV titanium dioxide with ozone, and and the study also showed previously significant removal, like making that research with ozone with UV and titanium dioxide. Though some unintended consequences could be happen by the oxidation of PFOA and PFOS. The plasma reactor can be more better. Dr. Lopez also investigating that possibility using the production of aqueous electron and hydrogen radicals, which can degrade the reactive species, the degradation of PFAS. If we look for the treatment technology feasibility of PFAS, in this graph, the study showed the range of practicability from non-viable to feasible, and the stage of development of those technology from experimental to mature. We would find that the advanced oxidation processes and photolysis are a prospective future for distracting or destroying PFAS along with the electrochemical oxidation. For that, in Dr. Medved's group, we are investigating the PFAS electro-oxidation, where we found that the electro-oxidation can be having adverse impact with the other water constituents, which is organic matters and inorganic matters. But we also, the study also found that it can be removed efficient way with the more hydrophobicity because of high concentration of NOM in the source water. We are also looking at the degradation pathways and the competition between the PFAS-6. And this study very exciting, where Dr. Medved are investigating significantly to find out the pathway more deeper way. We also doing collaboration works with Mass DEP with other universities, and this is the program we did and started from 2020 July 1 to July 30, 2022, where we tested public water system more than 1,200, and we found 53 of the raw water source is below 2 nanogram per liter or parts per trillion. 35% is in between 2 ppt to 20 ppt. Unfortunately, 12% of the public water system was exceeding 20 ppt maximum contamination level. In total, 60% sample collected for the community participant PWS is detectable level is below 2 ppt, where the major PFAS-6 also below 2 ppt. In the finished water, we found 161 public water system is above 20 ppt MCL among those 1,200 participant water system. We also looked in the public private well system around more than 1,600, and majority of the well around 70%, 73% are resulted below 2 ppt. That result and well published in the Mass DEP website, and the detailed result and the report can be found there. And we are also investigating our time to see the newly proposed EPA rule can put a significant economic and disproportionate impact on marginalized community. So we are trying to assess that impact and trying to find out that setback to make the study broader range to comply the EPA regulation upcoming. With that, I want to shift the little bit challenge we are having in the lab for quantifying the EPA, for quantifying the PFAS. As in this picture, I'm showing the mass spec, which is can be contaminated, and deep core of the mass spec with the tandem MSMS, if we are not properly pre-process our PFAS water sample, and we were not able to measure PFAS sample for quite a bit long time because of those longer chain PFAS was contaminated our system. And at last, we are in the point that we can go further deep research after tackling that challenge. With that, I want to thank you, Dr. Lopez, Dr. Macbeth, and Dr. Rakau for all those novel and exciting research that are happening in UMass for those forever chemical treatment processes. Thank you all.
Thank you, Kiran. So I just want to remind, if you have questions, you could always add to the chat box so that our panelists can directly respond to that. So our next speaker, Dr. Monica Hubbard. Yeah.
Oh, great. Thanks for having me. Hopefully everyone can hear me. My network is a little slow today, but I think it's because it's finals week and everyone's dealing with that. I myself am dealing with it. Today, well, a quick introduction. I'm Dr. Monica Hubbard. I'm here at Boise State University, and I am within the School of Public Service, and I study like policy changes within emerging contaminants and other things, including public lands, dam removal, and all the good things. So today I'm going to talk and focus on contaminants of emerging concern, but specifically pharmaceuticals. Oops, just one second. Let me share my screen first. All right. Hopefully everyone can see that.
Yes.
Okay, great. So I'm going to talk about active pharmaceutical ingredients, which effectively are just any part of the drug that produces its effect. And one of the concerns that at least government, when I say government, I'm focusing mostly on some national governments of state and local governments and how they've been trying to manage and deal with these things. And I'll go over the source and the fate, but you already did that a little bit. Some of the externalities that we haven't discussed and really play a role in why these are wicked problems per se. And of course, what we're doing. As you already know, this is a very general diagram. It does not include septic systems or manufacturing, anything like that. But I'm going to focus on the disposal of unused pharmaceutical drugs versus the pathway of how we metabolize it out of our system and into the wastewater treatment plant, but mostly disposal. And of course, there's kind of three ways we talk about within the sink, the toilet, flushing it, household waste, and then the pharmacy, whether or not that actually is an option. And as some of you may have already found out, it is not really an option as far as disposal of unused drugs. So where are we seeing the sources of unused pharmaceutical drugs in their solid state? Hospitals, of course, long-term care facilities, veterinary clinics, including cute ones like Dr. Paws, like that, agriculture, schools. What happens actually in schools is children or kids have medications. A lot of them are actually controlled substances. And the end of the year, the parents just leave them. So they have a stockpile of these medications at the end of the year. And residential households, which is what I'm going to focus on today. How much are we talking about? You know, a lot of people are like, most of the drugs or the active pharmaceutical ingredients we see in our waterways are metabolizing. We're not really sure because there is quite a few that still inhibit our system. Within the United States, there's about 4 billion prescriptions a year just out of retail pharmacies. This does not include hospitals or so on. And that's about 12 per person within the United States. And one study found that only 2% of the US population actually uses all their pharmaceutical drugs. And about 2/3 were actually only partially used. So we're talking about close to 3 billion prescriptions a year that aren't used. I should put on there, Pharma did their own study in 2006 and actually estimated that 20% of pharmaceuticals aren't used, which is kind of inverse of all the other studies that actually looked at some of this. Negative externalities. I'm kind of flying through all these so we can kind of get to the fun stuff, the public policies, and we've already touched on some of those. Number one, High School Musicals. It's always a challenge. Water quality. Some of you have already mentioned the water quality issues with active pharmaceutical ingredients, but this one study that USGS produced in 2020 really was a focusing event for a lot of subnational governments, state and local governments, when they realized their systems had pharmaceuticals in it, and there was really concern about what this could mean as far as a regulatory regime that might come out of it. And of course, we found that those pharmaceuticals, even in small streams that don't have any wastewater, receiving wastewaters, and in primary drinking water sources, which is a concern for drinking water providers, by drinking water sources, most of that is like groundwater. So we're showing it there as well. Tissue accumulation, I'm not going to go into that because some of you already talked about it, but of course, seen everything from like skin deformities and amphibians. And as we move up in the food chain, we're finding more and more farm APIs in the tissues. Fish abnormalities. So when we're talking about feminization of male fish, this was also a thing that government realized it could be a problem. And here in the Pacific Northwest, we are, of course, are dealing with endangered species that are trying to recover, and pharmaceuticals are actually impacting a lot of these endangered salmon, especially like Chinook species, as we're trying to deal with that. And what's happening is, of course, the feminization and deformities to a lot of these fish species that a lot of these like Fish and Wildlife and Fish and Games are trying to deal with. Unintentional poisoning. About 300 kids a day go to hospitals from accidental poisoning from pharmaceuticals, which they usually get within the household. On average, 2 die a day from accidental poisonings. And by the way, this is not me. This child is much cuter than I am for that. Misuse of farm parties, PHARM parties. There's, of course, we keep hearing about the opioid crisis, but in the 2000s, there was a big increase in farm parties where people would just kind of go in and throw all their drugs that they find within a bowl, and then, of course, go from there. And one of the things that I've discovered is like about 80% of new heroin users actually started with prescription drugs. So, and I'm not even just talking about controlled substances, prescription drugs, but any prescription drugs, which they almost always get from family and friends from there. And of course, human health impacts, which you've already kind of covered, but there's been studies around human health impacts. One is actually the nocebo effect, which we don't hear a ton about, but there has been research showing that people feel like if they've been exposed to pharmaceuticals within the water, that they might actually get ill from it. This meth gator, it's a real thing, but not a real thing. Some of you might have heard about it in Tennessee. A sheriff department basically said, don't flush your unused drugs because you're going to produce meth gators. This, interestingly enough, put pharmaceutical drug disposal on the public agenda, and the public started actually thinking about unused drugs. Unfortunately, a lot of people did think there were meth gators, but there actually are no known meth gators yet, unlike Cocaine Bear or whatever that movie was. So this is actually something that's driving a bit of the public. So what is happening as far as a regulatory framework? How are these unused drugs actually regulated right now? And then what is the concern about potential regulation? And the potential regulation is what is driving these governments to try to deal with these unused drugs. Currently, pharmaceutical drugs are regulated under two main regimes. The Resource Conservation and Recovery Act, RCRA, handles hazardous waste. And anywhere between, the estimate is between 5 and 15% of pharmaceutical drugs are considered toxic or acutely toxic, meaning the transportation of these drugs have to be used by licensed carriers. They can't transport toxic drugs. So that limits what can happen with them. And the other, of course, is a Comprehensive Drug Abuse Prevention and Control Act, which some people call the Controlled Substances Act. And that controls, basically creates this closed loop system with controlled drugs. Where to go? Here we go. So some of you might have heard about this system, others may have not. What does that mean, closed loop systems? Pharmaceutical drugs, yeah, the estimates vary, but some say it could be up to 20% of pharmaceutical drugs are on the Controlled Substances Act schedule, either 2 through 4, meaning, you know, that the talk of like, well, just take it back to the pharmacy. Pharmacist itself, once a pharmacist gives you your drug, it is out of that closed loop system and they can't take it back. Your only option is to take it to law enforcement. I can answer questions about that later. Law enforcement is not a great option for this. But as a result, pharmacists, just because of they won't take back your unused drugs because there's a chance you may have a controlled substance in it. So that kind of locks it up with that. So with these two regimes, it makes it very difficult for government to deal with unused drugs. And of course, the third thing that is popping up that is a concern is the Safe Drinking Water Act. You know, we recently just saw the forever chemicals listed on there, but pharmaceutical drugs, I think in 2016, EPA placed 10 pharmaceutical drugs on a contaminant candidate list. So we'll see what happens, but that has local governments kind of shaking in their boots a bit about what would happen if these are actually regulated under the Safe Drinking Water Act. So how do people actually dispose of pharmaceutical drugs? I already mentioned that most people actually either stockpile them or they try to get rid of them in trash and so on. So a lot of these studies found that one study found about 92% of people don't dispose of their unused drugs. They stockpile them in the house because they have nowhere to take them. Others found that majority either throw them in trash and or in the sewer, which kind of is a challenge, right? Because these regulatory systems of the clean of RCRA and the Controlled Substances Act have kind of created these institutional barriers to disposal. So we're kind of just seeing people stockpiling them. If they do throw them away, it's in the trash and sewer, which creates the other challenge we're looking at. So there's kind of a functional dilemma that government has dealing with, and that is basically, do they throw it away? Do we allow people to throw it away, which leads to the problem of water quality issues, or do we let them stockpile it? So there's that big challenge. So what has been happening since the early 2000s, which you don't hear about. There's been some innovators within government. Maine was one of the first ones to actually pass legislation about unused drug return, but it kind of died in the fact that it received zero funding for this program. So it was passed, nothing really happened with it. And then they also ran into the regulatory problem of the CSA and RCRA. And then within the state of Washington, Clark County was the first, and their policy window, they were looking at prevention of drug disposal in the thought of that these could be regulated under the Safe Drinking Water Act. So they wanted to make sure they kept it out of the water, and they developed a pilot program, which DEA went in and terminated because of the Controlled Substances Act. Within that pilot program, when they kind of started looking and digging down on what kind of drugs were being returned by the general public, about 20% were Controlled Substances Act, and about 5% were considered toxic under RCRA. So Clark County was shut down from it. The state of Washington also tried a program, and they ran into the same thing. DEA terminated their program. So that was kind of happening throughout the United States. So as a result, certain governments, California, Oregon, Virginia, and I'm just putting a few examples on there, started pushing to develop a pharmaceutical return program that basically were stewardship models. And within these stewardship models, they would put the onus on the manufacturers and with the manufacturers within the states, aka pharmacies or pharmaceutical companies, to develop and fund drug take-back programs. And as you can imagine, pharma and other interest groups weren't too keen on this. And so they used kind of this policy window of the Bush administration at the time to try to preempt any of these state efforts to develop these programs. So industry went into the Bush administration. Within that, the White House put out an order or direction for the public on how to deal with unused drugs safely. And of course, if anybody's ever heard about it, they basically told the public to take their unused drugs, mix it in kitty litter, and then mix it in Coca-Cola, and from there, put it in the trash, which of course ends up in the landfill and a leachate problem. And then the Congress at the time allowed the DEA to effectively reopen the Controlled Substances Act and created the Secure and Responsible Drug Disposal Act of 2010, which sounds really great. But again, it was an effort to preempt state governments. And what this did was actually not quite a lot. What it did is it put the onus on local pharmacies, so privately owned companies, to deal with unused drugs. Within that, the pharmacies can go and work through the bureaucracy to change their DEA status to allow them to take in controlled drugs. They could either fund a mail-back program, which at the time the post office was a no-go for. They could develop a collection system, and this collection system, they would be required to put in the infrastructure within their own pharmacy for the collection, pay for a reverse distributor to come in and take the waste. And they also ran into security issues with drug seekers. And as you can imagine, throughout the United States, only a few pharmacies actually went ahead and did that. It was very few. And I'm just kind of an anecdote here in Boise. There was one pharmacy within the Boise metropolitan area for close to 750,000 people, one pharmacy, and their drug disposal looked like a little bit of a mailbox, but it was always full. So it really wasn't effective. This also created, which we've all maybe heard of, the National Take Back Day. It sounds great, like a DEA program, and that the DEA would actually fund it. That is not the case. The federal government did not fund these programs. Again, the onus was actually on the government and or private entity to actually produce these take back days. And what they found was the cost was astronomical. One small community, for example, in Minnesota, for one day, it cost them over $15,000, and plus the bureaucracy of actually doing it. So that's about $25 per car, and it was not cost effective, and it was kind of considered complicated and convoluted. And actually, the amount of drugs they took in were really minuscule. Near Bearson is actually disposed. And it also missed a lot of people who are homebound, ill, and rural communities, because there's only a few in certain areas. So what kind of happened after that is it kind of just sat there, the drug disposal. And then the federal government started putting out guidance on what to do with drugs. And there was kind of conflicting agencies with conflicting programs. The EPA, of course, was guiding people to not flush their drugs or throw them away, but to actually take them to a take-back location, which often did not exist in most areas. While the FDA was advising people to flush their drugs or throw them in trash, which of course leads into water quality problems. So we have these kind of conflicts on the national level, which of course the states and local governments were trying to deal with. Fortunately, but what has actually happened was the opioid crisis has kind of created a policy window for this kind of to come up again to deal with the issue of unused pharmaceuticals. And, you know, again, with a lot of the overdoses, like in 2016, about 2/3 of opioid deaths were actually contributed to prescription opioids. So that kind of led some governments to try to innovate how to actually deal with these unused drugs again, and in lieu of what was happening on a federal level. So again, it's kind of this tit for tat. State governments try to innovate, put in a program. Interest groups like pharmaceuticals, and pharmacies pushing the federal government to preempt whatever the states are doing to have a program that doesn't really impact them that much. And then we have the opioid crisis, which again, the states are using it as an opportunity to again develop a pharmaceutical drug take-back program to be a bit more preventative versus dealing with the outcome. So again, the states are what they're trying to do is prevent the drugs from getting in the water in the first place, while the federal government is pushing them to do the post and try to remove it from the water once it's in there. The state of Washington, and actually it ties into the governor of the state of Washington, who's one of the childs died from an overdose. Actually, was kind of the entrepreneur in pushing this, and they developed one of the first full state take-back programs in 2018. It's finally up and running. And it is a product stewardship model, which requires the pharmaceutical industry to actually develop the take-back program and fund these take-back programs. And so Washington did it. Other states are now looking at it. Since 2009, there's been over 70 legislative bills in state governments and within almost half the United States to deal with unused drugs. Now that Washington has their in place, California is working on one as well, and Oregon is also looking at this using the stewardship model. So I think what we're going to see is we're seeing more of a federal response, but it's pretty weak at this point. And I think a lot of it has to do with the Biden administration being in place. And really, it is just forcing pharmaceutical companies to pay for mailers for opioids, but only opioids. Anything else, they're suggesting people actually mail, and they can pay, you know, almost like $12 for an envelope to mail their drugs. But now that we have a new policy window with the Trump administration, a lot of us think what we're going to see is what happened with Forever Chemicals, pharma. And I think what we're going to see is the pharmaceutical industry is going to push EPA, who whoever actually ends up running it, we'll see. And the Trump administration to try to develop a federal plan that officially preempts the state efforts, which would shut down states, or they're going to try to push the federal government to put in legislation that would limit their liability associated with pharmaceuticals and in particular water quality. And I think we're going to see that. That is my prediction. But that's kind of all I have for today. Hopefully I stayed within the 10 minutes with that. Thank you.
Thank you, Dr. Hubbard. At this time, we'll be having a chance to ask questions to the panelists. And you can actually enter your questions on the chat box. So I'm going to read one of the questions to Chuck. Chuck, you are here. So there is a question from Javier. What strategies could countries like Colombia take to address these contamination problems, considering the lack of economic resources for monitoring and treatment?
Yeah, that becomes a real challenge in some countries for monitoring for these. You know, what in operating facilities adequately with the resources, sometimes like from looking at particularly water treatment plants and wastewater plants in South America, the resources aren't always available all the time to meet that quality of it. Perhaps the best situation to probably to do in those countries is to rely more on the traditional bacterial indicators for now. It depends how that water is going to be reused too. I think the best possibility for some countries is to use water treatment, treatment at the tap or treatment at the household, because the dependability of even the quality of water you may get in a distribution system may not be adequately treated, or the variability of that treatment is really great in a lot of countries. So treatment at the tap is your other option for the drinking water. We've evaluated a lot of systems. There's a lot of them available through different agencies, even UNESCO and that. And the World Health Organization now has tested and evaluated different water treatment devices for household use, or you can go to their webpage, and they found out which ones passed their criteria for eliminating viruses, bacteria, and parasites, and you can actually look at that. But I think that's the best option for the drinking water and treatment in that. I think wastewater discharges is more challenging in some regions of the world in that, and it's difficult because of the cost. It costs much more to treat wastewater than drinking water. And so that becomes a real challenge on that. It's not easily solved, I think. But for drinking water, household treatment, it would be the recommendation to me for a lot of, particularly in South America, which we've studied the issues a lot.
Thank you, Chuck. I'm just looking at the chat box for any questions, so feel free to add that one. But I just want to give an opportunity for the audience to share their experiences related to emerging contaminants. Especially on what type of risk they're facing, what type of approaches they had been pursuing, and also are they using any type of interesting innovative policies that they could share. So if you're in the audience, if you're willing to actually share, you can always raise your hand, and I will let you, I will call you in to share. There is a question on the, that's from Monica, I think. Go ahead and ask Chuck.
Yeah, I mean, this kind of goes to the policy area, but Chuck, since a lot of your research is looking at maybe the quote unquote toilet to tap, do you know if the state of Arizona per se has been interested in your research more so as of late, in lieu of the cuts in the Colorado River and some of the challenges there?
Yes, there are 5 cities in Arizona that want to go basically from wastewater to drinking water. They're actually developing the facilities for doing that, actually. And Arizona, as a result, because of the work we've been doing and others, requires pilot plant first and you have to quantify virus removal, and then you have to monitor your full-scale plant once a month for at least 2 years for viruses to back up that it's actually doing what the pilot plant told you to do. But yeah, Arizona is moving more rapidly than any other state that I know of currently for direct potable reuse because of the concerns. We're already short of water now in the central part of the state. So yeah, they're moving. So um, one of the things I saw another question you had on the groundwater is our recommendation is that they do a buffer zone, like put the water into the groundwater after it's like they do in California at Orange County, where they treat the water to a high degree and then they infiltrate it into the ground, and then it has a certain amount of resident time and pump it back up. That gives you a buffer. I don't think it's a good idea to go to direct potable use from a plant. I think you should have a buffer, a reservoir, store the water under groundwater to give it a buffer. So if you really need to treat it more or you discover a deficiency or variability, you have a buffer to take care of that. I think is the option, but certainly in the West, we're going to see a lot more push towards direct potable reuse.
Thank
I
you.
had a question for you, if I can ask it. I wanted to ask you about the excretion of the pharmaceuticals from individuals. How much of that is being contributed, or are you worried about changes in the body that might make it more of a concern? You know, like your body might change the chemical structure of a drug, and that might affect the environment. Do you have any sense for that from your work?
That is a great question, and one no one could really answer. There's a lot of actually challenges looking at how these drugs are metabolized, and one is the pharmaceutical companies would actually have to allow the research to happen with how much is metabolized, but the other is just a lot of different things like dosing the actual individual and so on. So there's that kind of point, like, you know, the research shows that yes, what's coming out of individuals it contributes, but no one really knows how much in comparison to the drugs that are just flushed and disposed of. So that's the real balance and challenge. And then when you look at some of these plans to try to have drug take back programs, the pharmaceutical industry, of course, is saying, hey, it's not from the drugs being thrown away. It's just what we, you know, excrete out of our system. And by trying to manage these, you're basically going to harm, you know, the elderly and the ill. So they're using that narrative to kind of try to stop that. So there's that part. And then as far as research, I think you might have asked this, like the pharmaceuticals with the APIs within the water system now, is that actually impacting humans? Is that where you're like the interaction effect? EPA has actually looked at some of this already, and USGS, EPA specifically has been looking at wastewater treatment plants and urban areas to try to determine the levels. And what they found is, I think they've only looked at 50 so far. Some of the levels are getting high enough. They're not there yet, but they're getting high enough that they are concerned about an interaction effect. So who knows? And I'm afraid what's going to happen is funding toward a lot of this research is going to evaporate, if you will, the next few years. So we'll see what happens.
I have a good question to Chuck, that the secondary, excuse me for my voice, the secondary metabolism could be put more interactive processes for modifying the PFAS in the environment, especially in ecosystem.
Yeah, that's a good. I wonder about that. You know, would there be modifications of it? You know, I don't know, but that's a good question. Or maybe not change the structure, but you know, it may be attached to another molecule or associated with tissues that are excreted, or cells or bacteria that may make a difference in its removal. But I don't know that much about the chemistry of the PFAS. So you got me for that. The concern is you're getting into the groundwater in Arizona, of course, but because of the long-term water reuse, but the water doesn't percolate much in the ground here because we got 100 to 400 feet to groundwater. So it hasn't seen much of an issue of groundwater contamination except near landfills or purposeful infiltration of wastewater. The big concern with wastewater in the West is we do a lot of recharge of water into the groundwater here for storage and treatment, and that puts PFAS in the groundwater. So the concern is that may stop. There may have to be limitations of recharging water into the groundwater for storage in the West, because that's a concern.
Yeah, I was wondering about when you recharge it, are you also aware of wastewater contribution to the unregulated DPPs like NDPPs or HAMs?
Yeah, that's a really good question. I don't really have an answer to that, but there is concern with that here.
So we have one question on pharmaceuticals. I think maybe Dr. Hubbard can answer that, on which industry is contributing the most in terms of residual pharma. I think they're seeing if it's domestic, veterinary, or agricultural.
Oh, that's a great question. And as far as unused pharmaceuticals, it's domestic. As far as pharmaceutical use as whole, like agriculture is a massive user, more so than like a veterinary clinic, but ag uses pharmaceuticals quite a bit, especially like antibiotics with it. But as far as unused, it's domestic, it's household. Hopefully that answers the question.
So, so I think this is about recharging groundwater, and I think possibility of removing contaminants during the recharge process. Maybe this for Chuck. When you answered that, could you also comment on the Sweetwater Wetlands program in Tucson, on how they do that?
Yeah, we have a large program here for what we call soil aquifer treatment or managed aquifer treatment. It does a very good job you can get a 5-log removal routinely pretty much for viruses here. It's not absolute, but the water is disinfected before it comes up. And it does remove a lot of contaminants from the water in that. A lot of them get like the phosphates and then are reduced because of absorption to the soil, for example, is one contaminant. And many of the organic contaminants are removed within the first few feet, actually, from recharge operations in that. And then they eventually, when the basins are dried here, they become aerosolized into the air in that too. Sweetwater wetlands is another system, is a tertiary system is used here for treating water and wastewater. It's using wetlands, as they call it, wetland treatment, which does actually a very good job of reducing a lot of the chemical contaminants because they're taken up by the plants. You usually have reeds or hyacinths or other types of trees that are even actually in wetlands. And it's another process. It does really good idea of removing a lot of the chemical contaminants, and nitrates in particular are removed by the plants and reduced from what we've seen here. The big problem with the microorganisms, the birds use it. So the birds contaminate it with salmonella and coliform bacteria. So you have to consider that. I think the risks are pretty low. But it does seem to do a really good job as a good tertiary treatment after you give, conventional treatment in that. What the process in the past would be, use the wetlands and then go into a recharge, because the wetlands remove a lot of the nitrogen and the phosphates. And so you even get a better process if you infiltrate that water into the ground. You do have more problems with clogging of basins, though, than you do with direct artificial recharge too, but it does have a benefit. Also, there's a big aesthetic benefit to the public too, because you bring in a lot of wildlife, particularly in an area that's a desert. It's an oasis. So.
All right. We are running out of time. I wanted to really thank the panelists for taking time to share your knowledge. And also, I want to thank all the participants who had been listening, but also interacting with the panelists. And before we disperse, I just want to mention that our next symposium in spring is going to be on compound flooding. So look forward to that interesting concept which is emerging on the water quantity side. So with that, thank you everyone, and we'll see you soon.
Take
Bye.
care.
Thank you.
Take care.
Thank you.
And, oh.